Hey folks, how's it going? This is Mr. Moray coming to you with a little video on Jiffy graphs quadratics. Okay, and what I mean by this is graphing quadratics in a Jiffy. All right, so basically what we're gonna do, okay, is in class we talked about what quadratics are, okay, kind of on a basic level. We talked about what they look like in the coordinate plane. They're parabolas like the ones you see here. Okay, and then we started to actually use some actual values for A, B, and C to create quadratics we could really graph in the coordinate plane. So we looked at a few examples of those. And if you haven't checked the video out on basic graphs of quadratics without the tricks, I'm going to go ahead and put a link to that. It should come up above. You should really check out how to graph quadratics on a basic level, like how to just plug in some values, get the x's and f of x's, and graph from there. So I really recommend you check that out. Okay, and so from our kind of somewhat investigation in class and our conversations and our observations, we came up with a few rules and patterns that we discussed, and then I thought I'd summarize here. And these are really, really important. And I think if you can kind of use these, they will help you make the graphing process easier. Of course, you're always welcome to make a table. I want to stress, you can always take numbers and plug them in, okay, and see what comes out. And if you do that, you're always going to be able to make a table and from there a list of points. What having access to these patterns helps us do is it helps us get there faster by finding the vertex very quickly, okay, and then using the symmetry to quickly get points to the left and the right of the vertex, okay? So in general, all right, a quadratic is any polynomial, right? Poly meaning many, nomial meaning terms. I guess we could say, not technically speaking, but we could say that here. Sorry, I'm just gonna go ahead and get myself connected. Okay. So, and in this case, it's quadratic because the biggest power of x is 2. Okay, and we call that the degree. Okay. And sometimes we say that a is not equal to 0 as well. Because otherwise it would not have this x squared here, okay? This is our first form, and we call that standard form, okay? So some of the patterns that we're going to see here will work for standard form. Well, they'll all work for standard form, but we're also going to learn about, I guess, 2 other forms. And so the symmetry and those ideas will still hold, but we are going to have to kind of maybe tweak some of our formulas here, okay? So I thought I would take a moment by getting started, okay, talking about some of what we've seen so far, okay? So the first thing is we have the vertex. The vertex is kind of like that meat and potatoes point, that really like important, valuable, like if you need to know a point, this is the one you want to know, okay? The really, really special. So, and that is because it is the highest or lowest point, okay? I'm just going to do PT. So it represents either the biggest value the function hits or the smallest value the function hits, okay? We now know from our investigation in class that in standard form, okay, I'm not saying this works in any other form. This only works when you have something that looks like this, okay? The formula to find the vertex is negative b over 2a. Some people say the opposite of b over 2a. I'm going to say negative b over 2a, okay? And we'll look at some examples of what that looks like. So that's what we have. Some people like their fractions written like this. X equals negative b over 2a. Just be patient with me. I'm working on a tablet here. Okay. All right, axis of symmetry. So every quadratic has an axis of symmetry. okay? And the axis of symmetry is this really special point, this line, that you can take one half of the quadratic and fold it on top of the other. Okay, so because we know we've talked about symmetry in the past, right? Okay, so it's the line. Let me just get that better. Through the center of the parabola. Okay, and now technically when we say center, bola. Sorry if that runs over there. So technically when we say center, we mean the vertex, essentially. Okay, it runs through that one special point. Okay, so here we'd have, this would be our line of symmetry. Okay, this would be our line of symmetry here, right? It runs through that special point, the vertex. Okay, you can imagine this running through the vertex. Okay. You will learn about other kinds of parabolas next year, but in course 1, we're going to talk about up and down parabolas. Okay, so in this case, you do have an axis of symmetry. We haven't talked about the equation in class yet, so I'm not going to talk about the equation here, but we will talk about that in class. Okay, the concavity, we did talk about that in class, so that is whether the graph is going to point up on both ends, right, down on both ends, right? We talked about in class, right? Do both ends point up? Is it like a happy face, see smile, or a sad face? Okay, so we discussed in class how the x squared holds the majority of the value of the function when you plug in a number of x. So for example, if I plug in, we talked about if I plugged in 100, right? That would be basically, this would be 10,000. This, right, because it's 100 squared, this would be 10, and that would be whatever it is, right? So likely, as x gets bigger, the x squared has the majority of the value of the overall output. And so it's the x squared that determines really what's going on when x gets really big or x gets really small, right? Because that's what the concavity is related to. So the concavity, in this case, we know that if a is more than 0, it's going to be a happy face. Think positive, happy. If a is less than 0, it will be a sad face. Okay, it will be point down in both directions. Okay, and so in that case, right, both ends go to negative infinity. Okay, and if you think about it, if you have a really negative value, if a is negative, well, whatever you're going to do to x squared, you're just going to turn it into a negative number. So instead of getting really, really large in the positive direction, it gets really, really small or really, really kind of large in the negative direction. It's pulled down because a is a negative number. Okay, and when you square something, you get a positive or a 0, right? So you're always going to get a negative number for this part if a is a negative number. Okay, end behavior. Okay, so again, that has to do with concavity. So if a is more than 0, okay, how we write it is as x goes to infinity, f of x goes to infinity. It's really always like that. As x goes to negative infinity, f of x goes to infinity. Because it's saying as x gets really big and then in the x direction, right, gets really, really positive, y gets really, really positive, or f of x gets really, really positive. And then when x gets really, really negative, y gets really, really positive as well, right? As we go negative, we're going up. So as we go positive, going up to infinity, negative down to negative infinity. Okay? All right. Now, what if a is a negative number? In that case, they're going to both point down. So you'd have this time as x goes to infinity, what's happening? F of x is going to negative infinity. It's going down, right? And the same thing with, okay, negative infinity, f of x goes to negative infinity. So see, the concavity and the end behavior match up. So first, you notice by the arrows that the M behavior is always the same with regard to your f of x. So in other words, it's either always going to infinity on both sides or always to negative infinity. So if you're writing this analysis out, you now know, well, look, I have to get either infinity, infinity, or negative infinity, negative infinity. How do I know which is which? Well, look at the graph. What's happening to the y values or the f of x values as x is getting big? If they're going down, then it's going to be negative infinity. If they're going up, it's going to be positive infinity. Okay. In class, we also talked about the change. So one student noticed that we started the vertex, and we're going to go up by 1, up by 3, up by 5, up by 7, up by 9. Now, we realize that only works when a is equal to 1. Okay? Because when a was equal to 2, well, now it was like 2, right? And then I believe it was 6, 10, 14. And someone noticed that essentially there was some pattern here. Okay, this was going up by 2, by 2, by 2, by 2, by 4, by 4, by 4. So what was the pattern? Well, we always know that there will be some kind of pattern to the change. And then we talked about, I showed you two formulas, 2ax plus b, which you don't need to know. Okay, this is just something that we talk about in calculus when we talk about derivative or change. It's like an extra thing worth knowing. But if you look at this, right, this is like a y equals mx plus b. So you can see that it's going to be a linear function. And what is the slope of this linear function? That's how much it's going up by, right? Every single time x goes up by 1, it doesn't matter what b is. This is going up by 2a, right? So that's interesting, right? So we talked about this constant second difference, right? The change of the change. So the change, first you're adding 1, then you're adding 3, then you're adding 5, then you're adding 7, then you're adding 9. So what you're adding is going up. You're adding 4, you're adding 4, you're adding 4, okay? So here's the thing. At the very minimum, you have to understand the vertex, acts of symmetry, concavity, and behavior. These are special, but if you understand the idea behind the change, if you really take time to understand these patterns, though the quadratics will appear different in other forms, the principles of the symmetry and the structure in the coordinate plane like these, those will always like be there, right? Those will always exist. So if you can find, I'm saying the vertex, even if it doesn't look like this, and you know it's a quadratic, right? So therefore you know it's a parabola. If you can find the vertex and you understand these patterns, then you really don't need to ever really plug anything in. And that's like kind of like where the beauty comes from with regard to quadratics. Okay, I really, really love this unit. Okay, so in this video, there's going to be a few problems. Okay, I've selected a couple ones where I'm going to do them in a little bit more detail. I've selected maybe a couple where I'll offer a little bit more input from you, and then there will be some where I'll ask you to do them and I will go through them step by step. All right, so this might be a good time, like if you need to take a break or anything, like pause and take a stretch break to do that. But like there will be links in the description, hopefully, so you will not have to, like, I definitely can understand if you don't want to go through like a 50-minute movie or whatever it ends up being. I want to make sure like this is a valuable experience for you. Okay, so take a second if you need to, and then I'm going to get started with how do we analyze something like this. All right, well, so thanks for sticking with me. I really appreciate that. I'm now going to jump into one that I'm going to do. Okay, so in this, I'm going to really kind of expand upon where we started with quadratics. So when we started with quadratics, we were like, okay, I need to build a graph of this function. So what does building a graph of anything come down to? Well, it's essentially drawing me a picture of all of the combinations of inputs and outputs. That is, numbers that I plug in for x, and when I evaluate, what comes out for f of x or y. Okay, I use them interchangeably in this picture and table. So if you can make a table of x and f of x values, that is going to directly get you to your graph. Okay, so what I'll tell you is very often something I would give you would be a graph and a function. I'm not going to give you a table. This is a skill that you need to develop, because I'm telling you, if you have me next year, I'm going to tell you to make a table, because that's your starting point. Okay, if you can make a table, you're going to get some combinations of numbers that will help give you some clues as to what's going on. So remember, we started with the idea of, okay, let's make a table. Now we're like, okay, so that, we can make a table, great. But that's often going to be a lot of work. How can I use some of these awesome patterns that I've observed about quadratics to be able to more easily determine some of these special numbers to plug in, so I can kind of save myself some of the time? Okay, so again, that's what I'm saying. If you understand these patterns, it will save you time, but in the end, you can always plug in, a bunch of numbers. The only other thing with plugging in numbers is you don't technically know that plugging in any of those numbers will give you something valuable. So for example, a lot of people are like, okay, I'm going to plug in 1, 2, 3, 4, 5. But if my graph is all the way over here, right, all I'm going to know is that, yeah, these numbers are way off. Those numbers are way off. And so I'm probably not going to want to be plugging any more points over there. Okay, so all right, so remember, the first thing we talked about is we have to find that special point, the vertex. So we talked about how the formula is negative b over 2a. So we need to identify some of the values, right? We have our a, which is 1, our b, which is 3, and our c, which is 2. Okay, so remember, this was like, we had an a, we had a b, and we had a C. Okay, so what we can do now is we can actually use the formula. Okay, so I'll do, here is going to be my negative. Okay, what's b? Well, b is 3. Okay, and it's all over 2. And what's a? A is 1. Okay, so it's negative 3 over 2, which is negative 1.5. Now, let's say you didn't think to plug in negative 1.5 because it's the vertex. Remember what I told you with this form, standard form? What's the easiest number to plug in? Just to give you a hint about how do I start this. What do we want to plug in? What we want to plug in, remember, is 0. Okay, so remember, I always suggest it's a nice easy point to plug in. You just look at c essentially in this form, and it gets you the f of x or the y value there. So that's a quick, nice, easy one. And you know what? If I'm asking you to find points, why not, right? It's a good way to get started. All right, so now I've got negative 1.5. Okay, and I need to plug that in. So remember, on your calculator, I'm going to show you how you would do this. Okay, so whenever you plug in, you're going to be plugging in like this. So this is a 1, so I'm not going to put anything. I'm going to put negative 1.5 squared plus 3 times 1.5 plus 2. That is how I'd plug it in. So the PEMDAS would be square it, multiply, add. Well, guess what? Your calculator knows how to do that. But, sorry, this should be a negative. But you have to feed your calculator the information so your calculator can get the right answer. Okay? So, here we go. Let's plug this in. So, this is what you do. You do negative. Okay, so the negative, remember, is down next to the enter. 1.5 squared plus 3 times negative 1.5. You can put a times in there, though it's not required, plus 2. Okay? On any common calculator that can do this kind of thing, like a graphing calculator that you would have access to, you will get the answer right away. Okay, so think about that as an option to you. Otherwise, you'd have to square 1.5, negative 1.5, so it would be 2.25. Then you'd have to do minus 4.5 plus 2. So this would be negative 2.25 plus 2. So it would become minus 0.25. Okay. Notice how you go from this, and when you do this, you get the opposite of it. That's an interesting pattern that often comes up around the time you find the vertex. Okay. So now I have negative 1.5, 0.25. All right. So, where to next? Well, now we have this negative 1.5, negative 0.25. So what this gets me is this, remember, this amazing symmetry. So what I know is that there's this invisible line right down the middle, okay? So that if I have a point that's on the line, or on the graph of the function, its mirror image, right? So it won't 0, its mirror image will always be on the graph of the function. Okay, it's perfectly symmetrical about a line that passes through the origin, the vertex, pass through the vertex called the axis of symmetry. Okay, I talked about that a little bit earlier on. Okay, so what that allows me to do is it gives me a 3 points. Negative 3, 2 is a free point on the line that I now get to like automatically like put on there without having to plug anything else in. That's really the amazing part of this. Okay, so what does this tell me? Well, I could plug in whatever I want, but I'm thinking, being honest with you, I'm gonna probably get a little bit closer because I'm gonna in this class ask for at least 5 points. So how about negative 1? I know negative 1 is going to be the same as negative 2 because negative 1 is 1/2 away from 1.5 and 2 is also, or rather, negative 2 is also 1/2 away from 1.5, right? Lower by 1.5 and then negative 1 higher by 1.5. So because they're the same distance away from the x of the vertex, their f of x values have to be the same. If you don't believe me, right, you could always plug it in. So if I do negative 1, okay, see what that looks like. So I do it on my calculator, negative 1 squared plus 3 times negative 1 plus 2 equals 0. Nice. Okay, so therefore, negative 2 also, we have to have 0, right? I get negative 1, and then its mirror image also must be on the graph of the function. Okay? That's really important. Okay, so here's what I'm going to do. I'm now going to connect it to make my parabola. I do the best I can. 5 points should be pretty good. The more you make, obviously, the better. Okay? And there we go. 5 points, including the vertex. And notice this axis of symmetry, x equals negative 1.5. That is the axis of symmetry. Okay? So go ahead, and if you need to, I know this has been a pretty long segment, go ahead, pause, rewind, go back, and make sure you understand everything I just did here. From finding the vertex using the formula, that we talked about in class that we kind of discovered a little bit. So you're getting some quick points and using the symmetry to really fill in the graph by doing more with less. Okay? So please go ahead and rewind, make sure you understood what we did here, and then in a moment I will move on to another problem that I'll do a little quicker. All right, so here we go. I gotta do this one here. 2x squared plus 6x minus 5. Okay, so again, we're gonna do our formula here. So I have negative 6 over 2 times 2. Okay, negative b over 2a. So I have negative 6 over 4, which is negative 1.5. Oh, how clever. I'm going to mix this one up a little bit. Since we're in the video, I still have a chance to mix this up. How about this? Let's change this up a little bit. I'm going to call this, and we never know how this one's going to end up right here. How about we call this 8x minus 5. So I have negative 8 over 2 times 2. Okay, so this looks a little bit better. So it's negative 8 over 4, which is negative 2. So my x and my vertex is negative 2. Okay, so we'll have that. Now, remember, what's our nice easy point? 0, negative 5. Okay, so I plug in negative 2, two options on my calculator. Negative 2, negative 2. Now, here's where you got to be careful. 2 is the leading coefficient. So you do your 2, then your negative 2 squared. See how that looks just like plugging in negative 2 for x? Plus 8 times negative 2 minus 5. See what we get. Negative 13 is what we get. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's pretend here's where we live. Okay? Okay? So based on this, I have this beautiful symmetry again. I know there's an invisible line that kind of cuts through here. And I know that if I have a point on the graph, its mirror image will always be a point on the graph. In this case, it is negative 4, because negative 4 and 0 are both 2 away from negative 2. So their y's are automatically the same. Again, if you don't believe me, put it in. Okay, now, I think I'm going to be in trouble if I graph negative 1. I have a feeling it's off the graph. So what's another easy number to plug in? I would plug in 1, because I know, look, 1 is a nice easy number to plug in. And what's my free point? Well, 1 is how far away from negative 2? It's 3 away from negative 2. And what other number is 3 away from negative 2? It's negative 5. So therefore, because negative 5 and 1 are both 3 away from negative 2, and remember, this is the vertex, because these are the same distance away from negative 2, they must have the same y. So now, or f of x, so now we have an option. Plug in 1 or plug in negative 5, but either way, once we get 1, we automatically know the other. So I'd like to plug in 1, because I think 1 is, in my opinion, the easier number to plug in. So I'm going to plug in 1. Okay, so I do 1 squared, which is 1. 1 times 2 is 2. 8 times 1 is 8. And then the minus 5 comes through. So this is 10 minus 5, which is 5. And now I know. Interesting, right? So this one's going up by negative, let's see, negative 5 to 5. It's going up by what, 10? Interesting. Okay, and then I get my free one, negative 5, 5. Okay. Now this graph is a little narrower. Okay? And as we remember, if you look at this function right here, the 2x squared, remember, that is where most of the value comes from. So if we look at this, right, if you have a number, if x is just 1, we already know, or rather a is just 1, we already know we're going to see it go way up really fast in the left and the right. So if the a value is more than 1, like 2, it's going to make the y values, the f of x values, go up faster. So what we see is a vertical stretch. Okay? Or I guess some people would see it as a horizontal being pushed in. That's another way that some people will look at it. Right? It's being put, but I see it as it's being stretched up in the form of the y values are increasing much faster. You see more explosive growth. But what's interesting about this is that you still have these really cool patterns where you're going, it looks like up by 10, and then I believe from negative 13 you would go up by 2, so you go to negative 11, and then right you'd go up by 6, so you go plus 2 plus 6 plus 10. So the difference, right, 2, 6, 10, well, this is going up by 4, this is going up by 4. So when I come to here, I'm going to be adding 14, and this will give me 19. And then since I have 2, I automatically get negative 6, because look, 2 is 4 away from negative 2. It's 4 more than it. Negative 6 is also 4 away from negative 2. It's 4 less than it. And because 2 and negative 6 are the same distance from the x of the vertex, their f of x or y values have to be the same. This is a fundamental thing we have to understand about quadratics. Okay, so this kind of is going to bring us to the end of the I do's. Please make sure you understand this and the previous one. Go back and look at any of the previous timestamps if necessary, or maybe even skip forward. And then in a moment, I will move on to the next set of problems. All right, so what I have here is I have this function right here, and I have f of x equals 1/2 x squared minus 5x plus 7. Okay, this is a challenging one because a is a fraction, but that's okay, right? So where are we going to start? Where could we start? We have 2 different points that we could find first. What's one of the points we could find first? And what's the other one we could find first? So one of them should have been the vertex, and the other one should have been the y-intercept, right? So the y-intercept, boom, 0, 1, 2, 3, 4, 5, 6, 7. The vertex is, what formula do we use? Negative b over 2a. Okay, so here's our a, our b, and our c. So it's going to be negative, okay, but then our number is negative 5. Okay, that's our b. Over 2 times a half. Okay, so let's think about this. Minus negative 5, that's going to give me 5. 2 times a half. What's 2 times a half? 2 halves. A whole. So we get 5 as the x of our vertex. Nice. So what this means is, what other number, so this is the vertex, what other number will have a y of 7? it will have a 0 in it, and it will be 10. And I know that because this is 5 less than the x of the vertex, and this is 5 more. And because these numbers are the same distance from this x value right here, the x of the vertex, their y values must be the same because of the symmetry. So now I need to figure out what is y when x is 5. So let's come to my calculator. Here's how we do the fraction. 1 over 2 close it in. And remember, your calculator understands how to do these order of operations. Okay, so take advantage of that if you have it. So your calculator knows, okay, I'm going to square 5. I'm going to multiply it by a half. I'm going to multiply -5 by 5. I'm going to do that, those two, do that difference. And then I'm going to add 7. All right, it knows the order of operations, right? So we get as -5.5 for our y. Okay, so, and by the way, -5 squared, 5 squared is 25. So we have 12.5 minus 25 plus 7. Notice 12.5, if you subtract, that goes down to -12.5. So see how you do that to the opposite? I found that's a pretty good pattern for when you have the vertex. See if you get the same thing when you plug it in, going from that to the opposite as you go from left to right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, not 5 though. 5 and some change. 3, 4, 5, 1, 2. Okay. So what do we plug in now? Well, a good value, what's a nice easy value to plug in? I'd like to plug in 1. 1 is nice and easy to plug in because if I square 1, I get 1. And if I multiply 1 by a half, I get a half. If I multiply 5 by 1, right, just get 5. So it's -1/2 minus 5 plus 7, right? Plugging in 1. 1 times anything just gets you itself, okay, including 1. So 1/2 minus 5 is -4.5. And if I add 7 to -4.5, okay, I get 2.5. So, what other one has to have a similar or the same y value? 1 is 4 away from 5. What other number is 4 away from 5? It is 9. Okay, so it has to have the same y value. Okay, I want to get a little bit closer. So I'm going to plug in 2. So 2 squared is 4. 4 times a half is 2. 2 times -5, that's -10, plus 7. So this is -8 plus 7. It's -1. Let's see. Wait, 2. Yes, 2. 4, 2 minus 10 plus 7. So what other one's going to have the same y value? Well, it's going to be 8. 64, so I would have 8 minus 40 plus 7. Sorry, 8, 32. Sorry, because it would be 64. 32 minus 40, negative 8 plus 7, also negative 1. Okay? Now, can I get closer? Of course. I can even go as close as 4 and 6. Those will be the same. I'll plug in 4. 4 squared is 16. Half 16 is 8. 4 times 5 is 20. Plus 7. So it's negative 12 plus 7. So it's negative 5. Okay? So that kind of helps you see it's this really kind of blown out graph. And so see how the more points I have, the easier it is to actually, and I'm probably jinxing myself as I say that, but the easier it is for even me with like a really imprecise tablet to make a graph. Now, here's the thing. I'm not saying you have to have all these points, but I would like you to have a good set of points that has gives me a very well designed parabola on the graph. For certain, you need the vertex, and you need at least 4 points other than the vertex. Okay? And then the graph has to be relatively accurate. If you get lazy, here's the thing. The y-intercept, I'm telling you this, is so straightforward to get. If you get lazy and you just have it shoot off and you kind of miss the y-intercept, that's not going to really personally fly with me, because you should be able to get those straightforward 0, 7 and get a sense of where the graph's going. All right, you can do this. Don't sell yourself short there. All right, so go ahead and make sure you understood this first one, and then in a moment I'll do the next redo problem. All right, so here's another one that we're gonna do. I'll go through this one a little bit faster for your sake, so you can get through this without hopefully pulling your hair out. All right, so now here I am. Notice the negative here is going to have a different impact on the graph. So let's do our formula. We have x equals what? Negative b over 2a. Let's find our vertex. So b is negative 4, so it's minus negative 4 over 2 times negative 1, because that's negative 1 is the a, negative 4 is the b, right? A, b, c. So we have 4 over 2, which is going to be 2. Now see, it's going to make sense because actually this is negative 2. So you should get negative 2. And it's kind of makes sense, right? Because if you have a negative b, well, if b is negative, it becomes positive. But then look, a is negative. So when you divide this, it should end up becoming negative again. So negative 2. So we're over on this side of things. Nice. Okay. So what's our easy point? You have to have this right on every single graph. You need to have 0. Okay, 0 goes with 5. Okay. Hopefully by this, time we're done with this, you're getting the swing of it. Notice my minimal use of the calculator. The less you can do with the calc, the better. I promise you. I know you want to, but I promise you that it will help you to be able to do it without a calc. Okay, I promise. You got to trust me. Okay. Now, negative 2 represents that special kind of symmetry. So what other x has to have the same y as 0? Has to be negative 4, because 0, these are 2 away from each other, and these are 2 away. And remember, that works only because negative 2 is the vertex. So these are the same distance away from negative 2, so their y's have to be equal. Okay, we know that about a parabola. Okay, so negative 4 also has to have a y of 5. Now, negative 2, here's where we have to be careful. So here's what it looks like. So I'm starting to see, again, some of the things I warned about with the calculators. Please make sure you are very methodical if you're going to plug it in without a calculator. So notice, Remember that you are squaring before multiplying. So first you're going to square, it's going to give you 4. But this is a negative or a minus or an opposite, so it becomes negative 4. Here you have minus 4 times negative 2, so these together, right, a negative and a negative, this gives me 8, and then I add 5. So notice the negative 4 plus 8, notice again, interesting, okay? 4 plus 8 is 12. Rather, negative 4 plus 8 is 4. I apologize. Negative 4 plus 8 is 4, and 4 plus 5 is 9. Getting a step ahead of myself. So here we go. Nice. So I now need to get a couple more values. Notice how the graph is pointing downwards, right? Because this is now the maximum. We can see points clearly below it, so it's got to be pointing downwards, right? Though we don't know what it looks like, we have what we know. If this is the vertex and these are points below it, then that means all the stuff's below it, right? It's always either going to be above the vertex or below the vertex, right? That's one of the special things there. So look, I know that two numbers are going to be the same. What two numbers close to the vertex are going to have the same f of x when I plug them in? The first one is going to be negative 1, and the second one is going to be negative 3. So if these are 1 away from each other, and negative 3 and 2, these are also 1 away from each other. So because negative 1 and negative 3 are the same distance away from negative 2, the x of the vertex, the y of their vertex must be the same. Okay, so let's plug that in. Negative 1 squared is 1. This makes it negative 1. Negative 4 times 1 is, negative 1 rather, is 4 plus 5. So that's 1. And I'm plugging negative 1 personally because I think it's the easier of the two. It's up to you. Negative 1 plus 4 is 3. Plus 5 is 8. And so negative 3 must also be 8. Now, notice I'm going down by 1. So now when the 1, 3, 5 looks like it's playing out with it, but it's going down. Instead of going up 1, 3, 5, because this is a negative, it's going down. 1, 3, 5, 7, 5, 7. See, if you take the time, if you honestly take the time to appreciate what these functions are and how these functions have this amazing symmetry that I'm really passionate about, then you can like not only make it easier for yourself, but you can generate these really beautiful graphs really easily, and you can have really good quality work that you can be proud of, but not really have to do that much digging to get that quality work. Okay, so please make sure you understand these, because in a moment I am going to move on to the you try problems. Okay, so now there's going to be a few for you to try. So each of these, what I want you to do is I want you to think about the process we just did. So you're going to take a moment, you're going to pause the video, you're going to try to find, ready, the vertex, maybe the y-intercept, and a few other points. So you need the vertex and 4 other points for a total of 5 points. Okay? So let's write this here. So what I need, vertex plus 4 other points for a total of 5 points. Okay? And based on that, I need you to come up with a quality graph and table that give me a sense of what's going on. Okay, so pause the video, find the information here, and then when you're ready, unpause, and I'll show you how to get the graph. All right, here we go. So I'm going to again start. If we think about our method that we've talked about so far, I've got 0, 7. Okay. All right, now I'm going to find the vertex. So I've got negative, the opposite of negative 8 over 2 times 1, because I've got 1 is A, negative 8 is B, 7 is C. So I have 8 over 2, which is 4. So 4 is the x of my vertex. And because the x of my vertex is 4, right, you have this line of symmetry at 4. So at 0 and what other one? 8 must have the same y value because of this symmetry. Okay? Now I'm going to plug in 4. So 4 squared is 16. Okay? 8 times 4 is 32. So again, notice 16 minus 32 to negative 16 plus 7, negative 9. 4, negative 9. Okay, now I need some more ones to plug in. This is not really good enough. So let's come up with another. What's the next easiest number to plug in? Work smarter, not harder, right? 1. Why not plug in 1? Not hard to plug in. And remember, because the vertex is 4, negative 9, if I know what 1 is, 1 will be the same as 7. Not 7 there. Aha. 7 below. Because 1 is 3 away from 4. 7 is also 3 away from 4. It's 3 above. 7 is 3 above. And 1 is 3 below. And since 4 is the x of the vertex, and 1 and 7 are the same distance from 4, their y's must be the same. So if I can just figure out what 1 is, I know 7 has to be the same as 1. So 1 squared is 1. 8 times 1 is 8. So 1 minus 8 is negative 7, plus 7 is 0. So I actually just hit, unexpectedly, the two intercepts. Now, what do we notice here? What's the change? 7. So imagine working backwards, right? You know the pattern is 1, 3, 5, 7, 9. Imagine working backwards, right? Like winding the tape back, right? So like 1, 3, 5, 7, 9. So we started here, right? Here we went up by 7. So to get here, how much did we go up by? Right? If we go back, well, we had to have gone up by 5. Then we had to have gone up by 3. Rather, down by 3. Then we'd have to go down by 1. So that's where the symmetry is helpful. Okay? So this is what you absolutely need to get, but look how this makes so much of a nicer graph. Okay? And using the symmetry, observe how I didn't plug in anything down here. Nothing here got plugged in. I just simply was like, okay, so it had to go 1, 3, 5, 7, 9. And I caught it. I was like, oh, there's the 7. So it went 1, 3, 5, 7, 9. There's the 7. So before it went up 7, it went up 5. So if it was going to go up by 5, the y would have to have been negative 5, right? Because negative 5 plus 5 is 0. All right, well, then it would have had to have gone up by 3. Okay, so if I go down by 3 and over by 1, right, that's where I'll have started. And that's this point right here. 5, negative 8. And then the vertex, down by 1. And then again, using the axis of symmetry, we get the other side. Okay, so please take a moment and pause if needed, but then in a moment, I will move on to the next one. All right, wow, so here we go. On the next you try here, we're going to have one where a is more than 1. We call this a non-monic, because monic means a is 1. All right, so go ahead, take a moment. Again, pause the video. Try to find the vertex. Remember, vertex, 2 points, and graph. Okay? So go ahead, pause the video. No, not 2 points, I'm sorry. Vertex plus 4 points and graph. Okay? So please pause the video, take a second to try to solve, and then in a moment we will go ahead and unpause and I'll show you how to solve it. Alright, wow, here we go. So I'm going to start by finding the which point, the y-intercept, now I'll find the vertex, so it's negative 12 over 2 times 3, which is negative 12 over 6, which is negative 2, and that makes sense. Because if this is positive and this is positive, well, negative b, this will be a negative. Well, this is a positive, so 2a will be positive, and a negative over a positive, well, that's a negative. Okay, so 0 is 2, so this is the vertex. Now, how far is 0 away from negative 2? It's 2 away. So how far is the other point going to be? 2 away. So it's going to be negative 4. Okay, so negative 4 will also be 7. It's kind of similar to this last one. Okay, so, right, negative 2 kind of hops. All right, but what is negative 2? So let's take a look. So here, notice how I plug this in. Notice how I plug this in. So we need to have negative 2 squared, which is 4. Now, a lot of people multiply first to get negative 6 and square it and get 36. You can see how this ending up being 12 and this ending up being 24, right? This is way different, okay? So it's really important remembering the order of operations, okay? So then I've got negative 12 plus 7, which is negative 5. Look how stretched it is. All right. Now, what other ones do I have? Well, what's an easy number to plug in? Should I plug in 1? I would say no, because look how bent it is. It's going way up, way fast. So 1 is unlikely to be on the graph. And in fact, I can see if we plug in 1, well, this will be 3 plus 12 plus 7. So if I plugged in 1, what I would get is I would get 22, way off the graph. So what could I plug in? Well, what about negative 1, right? Because if it's going off this way, well, negative 1 has got to be somewhere in here, okay? So negative 1 squared is 1 times 3 is 3. 12 times negative 1 is negative 12. And 7 is 7. It is what it is. So that's going to give me 3 minus 12, which is negative 9, plus 7 is negative 2. So which other one has to have a y of negative 2? Negative 3. So notice it's going up by 3. Then it's going up by 12, I believe. No, it's going up by 3. Then it's going up by 9. So notice this is going up by 3 times 2, which is 6. So the next one will be going up by 15, but as we saw, we got 22. So connect them. Got to solve a parabola. Okay? We only plot the points that can fit. Okay? So please pause and rewind if needed. Please make sure you understand what I did here. All right, and then in a moment I will move on to our final U-try. All right, last you try, we're going to do them with a negative coefficient. So again, what I want you to do is pause the video. I want you to find me the vertex plus 4 other points, and then I want you to graph. Okay, so pause the video, give me the vertex and 4 other points in the graph, and then unpause, and we'll see if you got it. All right, so here we go. First, let's get our easiest point. 0, 3. Now, let's do our vertex. So we have x equals what? Negative b over 2a. So it's negative 4, because that's a positive, over 2 times negative 1. Right? Negative 1 is our a. So it's negative 4 over negative 2. So it is 2. Okay? So look, remember, we have the symmetry at 2. So if I have to go 2 to get to the line, how far do I have to go away to get to the point on the other side? Another 2. So what point is this that I get for free? 4, 3. And isn't this weird? I've gotten this. I never plugged anything in. All I've done is just go, look, 0, 3, easy, right there. Negative, just do a little formula, and already, just by knowing that, I've gotten 2 of my 5 points already, and basically 2.5. The work's basically half done, practically. Okay, so now I need to find the y when x is 2. So I'll do negative 2 squared plus 4 times 2 plus 3. Okay, so here I'll do it in the calculator as well. So negative, and use this minus. You're not subtracting, you're doing opposite. Okay, 2 squared plus 4 times 2 plus 3 is 7. Which makes sense. It should be larger. Now, here's why it's important. Notice what would have happened if I had made that mistake and I had left off that initial parenthesis, right? It should make a difference. Let's see if it does. Sorry, I'll try it one more time. Negative 2 squared plus 4. So here I'm not going to put the parenthesis there. Interesting. So that has to be a coincidence. And in this case, I believe it is. This happens to be a coincidence because, okay, 2 and negative 2, right? I should get the same answer in the end. But here's where it generally can get frustrating in other ways. So you have to be really careful when you work with this stuff like this. So for example, if you plug in a negative, I'll show you. So if you plug in, say we're going to plug in negative 1. Sorry about this quick aside. So I have negative, right? So it looks like it's all right when you use the positives, right? I'm plugging the negative 1, right? But some people are like, all right, but look, these cancel. So it's just 1 squared. Okay, this is just 4 and a negative 1. And then, all right, I'll add the 3. 0. So these are obviously 2 very, very different answers, but only one of them is right. And it's the first, because see how I can clearly see the minus, I can see the parentheses, right? Everything is laid out exactly as it would look if you plugged it in, and the calculator, we can assume, has done the PEMDAS correctly, okay? So very important. Let's see if I can get the history back. Okay, so we got 2, 7, perfect. 3, 4, 5, 6, 7. Totally planned. Okay, easy number to plug in, 1. Okay. So -1 squared is not the same thing as squaring 1 and then making it negative. Okay? Because look, I'll show you this difference here. Okay, here's the right way. So you square 1, you get 1. This makes it a -1. Here it's just adding 4 and 3. So this, you would get 6. What about here? Well, here you'd square 1, you get 1. You'd minus the 4. Or maybe you'd assume, let's say you're assuming you'd add the 4 and then the 3. Here, you'd get 8. So if you'd accidentally moved the -1 in here and not done it here because you'd gotten mixed up with the negative stuff, you would actually get a completely different answer. So it's important that you set up your parentheses very carefully, whether you do it on the paper or a calculator. So when I got 1, I got 1 squared is 1, make it negative, -1, plus 4, plus 3. Okay, so that's 6. So which other one is going to have a y of 6? It will be 3. Okay. Now I'm going to go ahead and form our parabola. Okay. So what am I doing here? I'm using the essential kind of basic symmetry that we know is going to apply across the board now. I'm using that to make doing the graphs a Jiffy. Now I know this has been a long movie or a long video and it's kind of contrary to what you think of when you think about Jiffy, but if you think about it, I'm no longer just plugging in numbers randomly anymore. I'm only plugging in the numbers that are going to get me the answers that I need quicker. And now I'm able to do that whether the graph is on the right or the graph is on the left, where plugging in 1, 2, 3, 4, 5 wouldn't do anything, or the graph is way on the right, so plugging in -1 and -2 would not do much, right? No matter where the graph is, no matter what the graph looks like, we have these patterns and observations that let us get a sense of what's happening starting at the vertex and going on. And we can even use these patterns to find the vertex. Okay, so I really appreciate you taking the time to watch this video. Okay, please make sure like it's here for you to use, but it's only as useful as you make it. Okay, so keep working at it. I definitely know you can do it. All right, stick with it, and remember, as I always say, you can do it. All right, thanks for watching. Feel free to subscribe and subscribe to alerts so that you can get the new videos that I post. And have a wonderful day. Don't forget to love math.